Thank you. I'll begin. Dear Father, we thank you for this weekend and time to relax and refresh. Let's pray you be with us today. Help us to, again, Lord, to glorify you in what we do. We thank you, Lord, that you love us even when we don't love you. And we thank you that you're a good God that you are, Lord. In your name I pray. Amen. Well, any questions? No questions. All right. So I'll give you guys the quiz tomorrow. But today I will talk about polar coordinates. So your next and final, well, it's not the final, but your final midterm, if you will, test 4 is on two main things: parametrizing curves, calculating things about parametrized curves using calculus, of course vectors, and two-dimensional vectors. And then the second major component to the test is polar coordinates. So let's talk about polar coordinates. So first of all, just the definition. If I pick, if I take any point here in the xy plane, and I can find the distance from the origin, call that r, right? And then this point can be shown to have coordinates r cosine theta, r sine theta. And that will still make sense whether we're in the first quadrant or the second or the third or the fourth, because sine and cosine are so arranged to give you the SIGNs that you want, as long as you use theta, the counterclockwise oriented standard angle. So we got some fundamental equations right here. So let's see here. First of all, we have x is r cosine theta. And we've got y is r sine theta. Right? Let's see here. Let's just do some algebra before we get too far into anything else. What's x squared plus y squared going to be equal to? So x squared plus y squared is r squared, right? So therefore, r is equal to plus or minus the square root of x squared plus y squared. So I would caution. Later, we usually assume that r is non-negative. However, when studying polar graphing and so forth, it is customary to allow r less than 0. I'm not a fan of it, but I can't avoid it, because it's in your book, it's in all the books, and many of the softwares that you study allow it. Yep. Oh, no. Just scratching, okay. Scratching is allowed. Let's see here. Let's see here. Before I get further down that rabbit path there, chasing that rabbit, what else can we say here that's kind of less? So we've got this, r squared, there's no ambiguity there. R squared is x squared plus y squared. We're fine. Everyone can agree on this. The plus and the minus, fine. There's some annoyance there. What else can you do? How about this? If x is not equal to 0, then y over x is what? R sine theta divided by r cosine theta, which is what? R's cancel, right? Tangent theta. So thus, tangent theta is equal to y over x. However, theta is only equal to inverse tangent of x for what? So if you think about graphically here, where is inverse tangent going to give you an actual angle that's between, where it should be. It's just in here, right? In this region, in x greater than 0, you'll get, inverse tangent of x, an element of minus pi over 2 to pi over 2, right? In there. Theta is not equal to inverse tangent of x in the other two quadrants, right? It's kind of a pain what happens over there. I mean, you have to, what I have to do? What would the formula be for theta? What's the formula for theta in quadrant 2? That's where x is negative, but y is positive. So that's my question. Can you guys tell me? I'll start you out. Inverse tangent of y over x. What should the target range of theta be? Yeah. Well, I suppose pi over 2 less than theta less than pi would be possibly equals here. Quadrant 2, right? It's up in here. Here's theta equals to pi. This guy is theta equals to pi over 2. So we're trying to... What do you just said add pi? I think that's it, right? If we add pi, does that make sense? The inverse tangent does what? It outputs between minus pi and pi over 2. If I add pi to that, that shifts it to where? Pi over 2 to 3 pi over 2, right? Oh, wait a minute. I can't do math. Oh, yeah, that's not going to do it either, is it? I don't think that's going to work, is it? I mean, I have here minus pi over 2 less than theta less than pi over 2, right? I mean, inverse tangent. Good grief, guys. Don't let me get away with that. These are supposed to be y over x, right? Sorry about that. So inverse tangent of y over x is between if I add pi to this, that gives me pi over 2 less than, oh, okay. I'm sorry, I'll get with it in a second here. I just, it's fine. I went further than I expected. I mean, this is good for what? Right. In other words, we went to find a formula for quadrant 2. I got a formula for quadrants 2 and 3, as it happens. Inverse tangent of y over x works for quadrants 1 and 4. Inverse tangent of y over x plus pi gives you theta for quadrants, again, 2, right, and 3 down here. Okay. So anyway, so there's the Cartesian. X is equal to r cosine theta. Y is equal to r sine theta. That's how to go from r and theta to x and y, right? On the flip side, if you want to take x and y and change to r and theta, it's a little bit trickier. Certainly, if you have x squared plus y squared, you can trade for r squared, right? And if you have y over x, you can convert it to a tangent theta, right? If you have inverse tangent of y over x, you can sometimes convert it for theta, but it depends on which quadrant you're in, right? Sometimes you need to add pi in order to get theta back. All right, let's look at an example here. Just to kind of warn you guys about the ambiguities here. So if I have the point 1, comma 1, right? Then find polar coordinates. When I'm doing these kinds of problems, I sometimes like to put like a little xy here to emphasize that this is the Cartesian coordinates, right? And then I want to find the polar coordinates. In other words, I want to find r and theta. But to be, I mean, I might put a little r theta there or something to emphasize I'm saying that's the polar coordinates. Because anyway, so what is r is equal to what? 1 squared plus 1 squared, which is square root of 2, right? And we're in quadrant 1, so I can use inverse tangent. Inverse tangent of 1 over 1, otherwise known as pi over 4. So, therefore, p is equal to root 2, comma, pi over 4 in polar coordinates. This is ambiguous, though, right? What else could you do? How about this? If I can find a marker. What if I use r prime equal to minus the square root of 2? What if I use theta prime equal to 5 pi over 4? Right? Then if you look at x is equal to minus the square root of 2 times the cosine of 5 pi over 4, what do we get? See, if you feed negative root 2 and you feed 5 pi over 4 into sine and cosine respectively, guess what? You're still going to get back 1 and 1, right? In other words, this polar coordinate, set of polar coordinates is geometrically equivalent, right, to minus root 2 and 5 pi over 4. I use this symbol here because I really don't think we should say equals, because they're not equals. These are different radius. It's different angle, right? They're different coordinates, and yet they geometrically correspond to the same point. Annoying, yes? I personally find this to be annoying. Now, part of this ambiguity, I mean, there's also another sense. This is also equivalent to what? Like root 2, 9 pi over 4. Right? Because I can keep the positive radius and add any multiple of 2 pi. Geometrically, that's the same standard angle, right? So this is an ambiguity we cannot avoid. You know, there's always this 2 pi multiplicity of the angle that we have to deal with. And in this chapter, we also have to be aware that if we have negative radius, it corresponds to adding pi to the standard angle. Okay? That's all. Okay, now that we've got that out of our system, let's look at more interesting things. So, generic task. How to go back and forth from the Cartesian viewpoint and the polar viewpoint. Right? What does it mean when it says find the Cartesian form of something? What's that mean? We only get to use x and y and functions thereof in the final product, right? On the other hand, this is just what? R and theta. Right? What's the bridge between these worlds? That's what I was starting with. I was showing you the rainbow bridge, if you will. So like, or you pick your whatever favorite bridge is, but let's see here. So these are how to go from polars to Cartesians, right? And vice versa, tangent theta is y over x, x squared plus y squared is r squared. That's how to go the other way, right? So we can look at examples. So let's just start looking at some examples. For example, what is r is equal to 2 sine theta in Cartesians? Right. That's a pretty typical polar graph. Polar graph is something like give r as a function of theta. All right. You could call that a polar graph. Let's see here. What I do when I'm faced with this question is, like, I like r squared, right? And because r squared is x squared plus y squared, which is ever so nice. And I also like to look for ways to create r sine theta and r cosine theta, right? So what I do when I'm faced with something like this is I just multiply by r. So either r is equal to 0 or r squared is equal to 2r sine theta, right? But anyway, I mean, I don't think anything much is lost. Certainly nothing's lost for non-zero r. If I just multiply that equation by r, so that gives me r squared is 2r sine theta, which is what? X squared plus y squared is 2y, right? Now, we complete this, well, move it to the other side. This is x squared plus y squared minus 2y equals to 0. And then you got to complete the square to see what it is. X squared plus y minus 1 quantity squared equals to 1. So, I mean, that's my final product right there. That's pretty nice. I mean, that's a circle, right? Circle radius 1, centered where? Looks like the center is at 0, 1, right? So here you go. I tried to draw a circle. I almost succeeded. Here, let me erase the evidence. So there you go. R equals to 2 sine theta is actually a circle. Radius 1 centered at 0, 1 in Cartesian coordinates. What if I just said 0, it's kind of funny. What happens here if you let 0 go to pi? I mean, suppose you just, I mean, this is interesting. If you think about 0 less than or equal to theta less than or equal to pi for r equals to 2 sine theta, it's not hard to see that that gets this whole circle, doesn't it? Because if I put theta equals to 0, it gives me r equal to 0, which is my starting point, right? What happens when I put r equals to, like, so here's your theta equals to 0, right? Theta equals to pi over 4 is like here, right? Up here is theta equals to pi over 2, right? And then what? This is going to be, of course, then, you know, this is 3 pi over 4. If you think about geometric. And so by the time I get to pi, I've gone all the way around the circle. What happens to pi to 2 pi? What's the deal with pi to 2 pi? Let me draw a graph for you for a second here. 2 sine theta looks like this, right? So sometimes it's helpful as you think about these things to look at a graph r equals to 2 sine theta, right? If I look at that, you can see what's going to happen. I mean, if you only allowed for r to be positive, you'd say, well, this is not physical, if you will, because that's negative radius. We don't allow that. But we do allow it, right? So what happens here is this is geometrically the same circle. It's just you have to make the identification like pi goes to 2 pi, right? And then like, for example, 3 pi over 2 in here, you add 2 pi, geometrically it goes to 5 pi over 2, which is the top of the circle. As you go from 0 to 2 pi, this covers the circle 2 times, is what I'm trying to tell you. So, all right, I think the more I talk about this, the more confusing it's going to get. So let me stop and talk about a different example. Oh no, this blue marker won't give up. Survive this. Oh, man. It's very stubborn. Can't resist the juice. Sorry. How about this? Example 2. If I have y equals to mx plus b for m not equal to 0, this is a line, right? Find its polar form. All right, this is really complicated what I'm about to do, so I hope you can follow me. Y is r sine theta. X is r cosine theta. And then we add b. I was being sarcastic in case you haven't figured it out. So here you go. Customarily, we solve for r, all right? And there you go. This is the polar form of the equation of a line. Ew, right? I mean, I hope your reaction is like mine. Ew. It's yucky, like not nice. Y equals mx plus b is so much nicer. Well, that's because a line, where is its home? The home of a line is where? It is in straight line things in the Cartesian world, right? And so if you take it outside its home, it becomes ugly. So I don't know. Maybe there's some kind of movie reference I could make. I don't know. But anyway, example 3. Let's see here. Now, if I have y equals to mx with m not, well, with m whatever, really, all right? Just that, m constant. Then this gives us m is equal to y over x, right? Y over x is what? Y over x is tangent theta. So this we can convert to tangent theta is equal to m. There's a polar form, an implicit polar form of this line. Where's r? There's no r here, right? It's not r as a function of theta. In fact, r is independent of theta. You know, if how to say this? If we're looking at x greater than 0, then we'd have theta equals to what? Inverse tangent of m. If x was less than 0, then theta would be equal to inverse tangent of m plus pi. Those are rays, right? Do you guys know what a ray is? So like this is theta equals 2 pi over 4, right? It just keeps going and going and going. On the other hand, this guy on the other side, down here, would be theta equals to 5 pi over 4, right? These are the two halves of the line y equals x. Together, in terms of Cartesians, together these give y equals to x, right? Y equals to x is the entirety of the line that goes on and on and on. In polar coordinates, it breaks into two things. Theta equals pi over 4 this way. Theta equals to 5 pi over 4 that way. Inverse tangent of 1 is pi over 4, plus pi is 5 pi over 4. All right. Example 4. Sometimes the Cartesian is just not familiar. For example, r is equal to theta. What does r equals to theta look like? Before I get to finding the equation of it in terms of Cartesians, let's just try to graph it. Okay? So there's a procedure here we can do. What we do is we plot theta versus r in a graph like this. And it's very boring. R equals to theta looks like what in the r theta plane? It's just this guy, right? R equals to theta. So we can look at, say, 2 pi, 6 pi, minus 2 pi. Oh, how did I get to 6 pi all of a sudden? What's wrong with me? 4 pi, good grief, minus 4 pi, and so forth. All right. I probably should blow that up. Let me blow that up a bit. When plotting polar curves, it's often helpful to make a graph in the r theta plane of the formula, if you can, and then use that to make the corresponding Cartesian graph. All right. So if I can, let me just try this again here. And I'll just try to blow it up a little bit. Say this is pi. Say this is 2 pi minus 2 pi. And here's my r equals to theta. All right, so I'm going to try to pick at just a bunch of points and plot those. All right, guys. So like, this is 1, and pi over 2 we'll do 2, 3, 4, 5. All right. Start with those. So here's my xy coordinate plane. I start at the origin, right? R equals 0, theta equals 0. By the way, what is theta at the origin? It's 0, it's pi, it's 2 pi, it's everything. It's nothing. It's undefined, technically, but if you'd like, if it makes you feel better, you could say theta takes on all values at the origin. Okay, but definitely r equals 0 at the origin. That's not, no one disagrees about that. So what happens when we get to 2? 2 would be at pi over 2, right? And so we're looking at a radius of like 1.57. These pictures, 2 pi is approximately 6.3, right? So let's set a scale here. Let's say that this is 6.3-ish. So that because I know that's the biggest thing that's going to happen on this graph, given my focus. So I'm just going to kind of start there. All right, pi over 2 is like 1.57. So I start at 0. When I get up to 1.57, that's something like this. This is where 2 maps to in the xy plane. How about 3? 3 is theta equals to pi. So that's more or less the midway point over here. That's 3. right? This was 1. Where's 4? 4 is about 3 pi over 2, right? That's down here. And 3 pi over 2, that's about 0.75% of the way to 6.3. So we're talking like here, roughly speaking. And then how about 5? 5 is back here, right? So let me try to graph this, looking at crudely speaking. That is just the part of r equals to theta going from what? Going from 0 to 2 pi. What happens when we go to minus pi over 2? I'll do this in red. So like here, minus pi over 2, this would be, let me call this 6. So I've got r equals to minus pi over 2, which is what? This is equivalent to r is equal to pi over 2 at theta equals to 3 pi over 2, right? That's the rule. If the radius is negative, then we take the standard angle and we add pi. So we have r equals to minus pi over 2 at theta equals to minus pi over 2. That's equivalent to positive radius pi over 2 at 3 pi over 2. So that would be what? This guy down here, right? So that's my 6. How about 7? 7, we have the radius is minus pi, theta is minus pi, so that is equivalent to r is equal to pi at theta equals to 2 pi, right? So where's that? That's like here, right? That's my 7. And let's see here, let's put 8 here. 8, r equals to minus 3 pi over 2, and theta is minus 3 pi over 2. That's equivalent geometrically to r is equal to 3 pi over 2, and at theta equals to what? Add pi, right? Minus pi over 2. Yeah, what did I do?
Isn't supposedly all equal to theta?
Yeah?
Like theta equal to minus pi over 2.
Oh, yeah. What have I've been writing? I wrote it, in the 8, down here I had it right. And so, oh man. Yeah. That's right. No, wait a minute. Yeah, let me make, man, I wish, dang it, pi over 2 here, right? And this one was what? Add minus pi, add pi, what do you get? 0, right? And this one, I finally got to doing the right thing here, finally. Okay, fine. Now, let's see, does that change my picture at all? Or did I get lucky? Theta equals to pi over 2. Oh, same point, all right. So that actually is 6 as well. All right, very good, thank you. Thank you. That saved us from having a disaster in about 3 minutes from now. 7, theta equals to 0. And this one is kind of funny. That's right still. Despite my earlier error, that ended up being right. That's a bizarre coincidence. Anyway, number 8, 3 pi over 2. So that's actually this point again, right? 4 and 8 are identified. Okay. And then finally, let's say 9. 9, we have r equals to minus 2 pi, theta equals to minus 2 pi. So geometrically, that's equivalent to r equals to 2 pi at theta equals to minus pi. So where's that? Theta equals minus pi. Sweet minus pi, it's over here. So that is actually this guy, right? Oh man, what have I done this time?
It's actually
Well, I don't think we disagree.
It's not theta equals to 0, but
Well, I don't think we disagree. I mean, minus pi and pi are geometrically equivalent.
I mean, like the minus 2 pi is like a rotation, one full rotation is the same as 0.
But negative radius means that this, yeah, I would agree minus 2 pi is here, but it's negative radius, so it's over here. Still negative radius.
It is still one more is the second one.
This is fine. R equals 2 pi, theta equals minus pi. It's that 9 I drew up there. And let me draw the curve, then it'll become obvious what's going on. So we're going from 1 to 6 to 7 to 8 to there. So this is the polar curve r equals theta.
Yeah, it's kind of messing me up when you rotate clockwise and
The clockwise versus counterclockwise-ness.
take the opposite.
Yeah, so this, I mean, personally, now my question is, what's the Cartesian equation of that? I don't know. I can tell you this much. R equals to theta. If you want me to just convert to Cartesian equations, I can do it like this. I mean, the square root plus or minus the square root of x squared plus y squared, right, is equal to inverse tangent of y over x plus epsilon, where epsilon is either equal to 0 or pi as appropriate. So there you go. There's the Cartesian equation of this. And it goes on and on. I mean, this is just the start, right? This keeps going and out and out. This is just the start of a spiral that goes both ways. I don't know about you. If somebody hands me the equation, the square root of x over y squared is equal to the inverse tangent of y over x, either plus 0 or plus pi, I don't look at it and go, oh, that's a linear spiral. That this doesn't, I mean, I don't see that personally. Not something I know, right? So, I mean, sometimes you take something that's relatively innocuous in polar coordinates, when you convert back to Cartesian coordinates, it becomes something completely removed from your experience, right? Sometimes you take something you know in Cartesian coordinates, you change it to polar coordinates, it becomes something that you might not recognize right offhand. Although, once I do this example, if I give you something like r is equal to 3 over sine theta plus 2 cosine theta, maybe if you thought about this example, you would know to see through my subterfuge and realize, oh, he's just giving me a line in polar coordinates. So once you see this, maybe you have some hope of recognizing a line, right? But anyway, that's basically it, though, guys. So we use the polar coordinate formulas. We plug them into the Cartesian thing to make it polar, or vice versa. The problem of plotting, you have to go point by point by point. Keep in mind the geometric ambiguity of negative radius being adding the angle pi, and that's a good bit of it. Now, there is of course more to say about polar graphing. It's also definitely worth your time to use a grapher. I think I still have some. My battery is a little bit sketchy, but I think we're going to make it. Let me try here. Desmos is pretty good. Let me show you some important examples of polar graphs. So like as we go on this week, we're going to learn how to calculate arc length in polar coordinates, or areas bounded by polar curves, things like that. But the stage one here is just to get our pause on like what are polar coordinates and how do they relate to the Cartesian coordinates. That's what we're doing today. Doesn't seem like calculus, does it? It's just sort of algebra mostly, right? And some graphing. These are actually really, really fun. Things like, what example am I on? What's that? 5? Say r is equal to the sine of 2 theta. Example 6. R is equal to the sine of 3 theta. Example 7. R is equal to the cosine of 4 theta. Example 8. R is equal to the cosine of 3 theta. Let's look at these. Now, I could go through the painstaking step-by-step process we just did, right? And I have in the past. If you watched the lectures from last year, you'll see I do that. And you need to do something. You need to find something, because I will ask you to graph a polar curve on the test, right? So it is important to understand the details of what I did over there. You want to be able to do something similar. Yes, please start graphing. I think. Let's see if I have. So Google. All right, let's see if I got one in here. I'll just take this one and play with this one here. So here's r equals a to the theta. Whee! All right, that's not what I want to do. Let's see here. So let me, I'm going to take their, come on. Stop that. What did I say? Sine of what? 2 theta. All right. Okay. I mean, where is it? Oh. No, this is no good. Sorry, guys. Give me a second here. Come on. Stop that. Stop that. Go away. Shoot. It's not at all what I want here. There we go. Let's start over. Graph settings. I want polar coordinates. Come on. Grid. Where is it? I'm sorry, I'm just not. That's a good idea. There we go. I just had the other one was on. The other one was doing like a parametrized curve or something, so it couldn't see it, or I don't know. Anyway, here it is. So here is the sine of 2 theta. As you can see, it's a flower with 4 petals. Right? What do you think happens if I make this 3 theta? How many petals is it going to have? Care to guess?
6.
You'd be wrong. Sorry. If I put a 4 there, how many petals? 8 is a good guess. Yes, in fact, 8. If I put 5 there, how many petals? All right, you guys got it. 6. Woo! 666. Oh, wait a minute. No, we shouldn't do that. Let's see here. 61. Ooh. Anyway, sorry, let me stop this. Sine theta is a circle. That's very much like my example 1. There's the example 1 right there, right? 2 sine theta. What if we make this a cosine? That becomes a circle over there. If I change that to 1, smaller circle. If I change this to 2, how many petals? 4. What do you think happens when we put 3? Yep, you're right. 4, yep. 5, yep. 6. What happens if you do like 2 plus cosine theta? Check this out. This is called a limicon, I think, if I remember right. A, add slider, yeah. Let's study what happens as you change that A there. Check it out. Yeep, whoa, whoa, whoa! What's happening? What's happening to me? You're torn inside out. Ah! Such violence. Look at this. Oh, Here, we should watch a movie of it. Being savages that we are. There you go. So all of these things are possible if you just look at something like 2 plus a cosine theta. It's got all these different polar graphs in there all at once. Neat, huh? These are enumerated and labeled in your text, right? They got names. I think limicon, and some of them are circles. Something with a dimple. I forget the names exactly, but they're all in there, right? So what we want to do here as we go on this week is learn how to do stuff like, I don't know, not that one, that one's too boring. This one here. Like, how would you calculate the area between this thing and that? Like, what would that area be? Right? Yeah, I don't know. But we'll learn how to do that. Anyway, guys, that's about all I got for you today. Unless you got a question for me. You got a question for me? You guys should be asking more questions, seems like. I don't know. What's that?